I'd like to introduce Christian Robert, who's going to talk about inference using the Wasserstein distance.
Right, so thank you for still being here. And apologies for missing the first half of the workshop. I've tried to be in two places at once, and it's a bit difficult. So what I want to talk about is using Wasserstein distance in ABC, which was not the original plan on the program, but given that Paul exposed earlier in the asymptotics of ABC, I didn't think you needed a repetition of that presentation. And so instead, I will talk about this work we did with Epstein Burton, Pierre Jacob, and Mathieu Gerbert, and the first two authors being the main workers on that project, with the idea being that in problems where you use ABC, it may be possible to get around this difficulty of choosing and validating summary statistics. So it's a very short talk, but I just want to give the intuition why you can use Wasserstein distances in such problems, give very few ideas about the asymptotics, and somewhat present something that really appears to me, that you can extend this notion of Wasserstein distances to models that are not the standard IID models, but rather dynamic models like time series. So, I mean, the setting is the ABC settings, where you have, say, a data set that is of any form, so naturally IID, that it comes from a certain generative model that well, you assume parameterized by parameter theta, and as usual, you want to find out what the value of theta is in a Bayesian way. So you want the posterior distribution of theta given one. So there's nothing new there, and we call it generative in the sense that it may be a complex model, but still we assume that the generation of new data sets like Z1 to N is feasible. So that's, I mean, the standard assumption when you run ABC. And so if you take the starting point of ABC before the introduction of summary statistics, in the standard notion for running ABC is this joint distribution on theta and Z1 to N, that again we assume we can simulate, that well, relates to the true observations, the Y1 to N, by selecting Zs that are close enough to 1. And I think I forgot the distribution. Well, I mean, this notation is for the joint distribution of theta and Z. Okay. And the Z is just an auxiliary variable that we use to replace the unknown likelihood, so that we have the ABC posterior distribution that is the margin of this joint. And I mean, the basic notion that makes it work or approximate the true posterior distribution is that this quantity operates as an unbiased estimator of the likelihood. And so in this formal framework, without using summary statistics, if we push the epsilon to 0, the tolerance down to 0, if we could do that, then we would recover the exact ABC posterior. Of course, in practice, you need to stop before epsilon is 0, because reaching this event is not feasible for epsilon equal to 0. And then, because that's complicated, we need to introduce summary statistics. Namely that I mean, this data set may be of quite non-negligible length, and to see that simulation close to the data set for a true distance maybe unpractical, or may reach a very large variance in the realizations, which means that in practice you cannot expect that to be feasible. And so instead, there is a substitute, which is to look at a summary statistic of the original data and a summary statistic of the simulated data, and use another tolerance that will be much smaller than that one to decide on acceptance or rejection of the simulated parameter. And in almost invariably, this summary statistic being insufficient, there is a loss of information compared with the original problem. But of course, the projection on a much smaller dimension space means that the variability of the estimation of the likelihood is smaller as well. And so there has been considerable work in the literature on the validation of this approach through summary statistic, namely when does a summary statistic provide a valid tool of inference for the estimation. But anyway, the one point is that even if we could reach epsilon equals 0, by using the summary statistic, we would definitely lose in information compared with the original problem. So we have an approximation even with no Monte Carlo error. And as Paul discussed earlier this week, you can very finely control the convergence of the ABC approximation based on the properties of convergence of the summary statistic, and you can connect the rate of decrease of epsilon to 0 with the rate of convergence of eta to its average. So the central tool is to control this convergence of eta. Okay, and so and that's the starting point for trying to do something else, which is that, of course, there is a strong dependence on the summary. There is a discussion on the impact of the dimension of the summary compared with the dimension of theta, with a sort of convergence to try to have the summary as small dimensional as possible, which is essentially the dimension of theta, even though you can prove convergence in other settings. But of course, there is still an impact of the summary that it's hard to assess in a complex problem, because you cannot run simulation experiments to compare summaries and check of the behavior of the ABC approximation in such cases. And so instead, well, we try something else. So in previous work with Jean-Michel Marin and courses from Montpellier, we tried to avoid choosing summary statistics through automated projection tools like random forests, which have the appeal of running on their own. They are automated, but of course there is still this projection. So even with a random forest, we do lose information from the data. And so the alternative is not to project at all, but to look at a distance between the original data set and the simulated data set that would be less valuable than well, the natural Euclidean distance that people use at the beginnings of ABC. Because in that sense, having a true distance between the data set and the simulated data set would ideally provide exact inference, in the sense that pushing epsilon to 0 would recover the true posterior. And so if we start with univariate data and IID observations, there is a famous result that order statistics are sufficient. So looking at order statistics instead of the original data does provide the same inference. And if we have a distance between the order statistics of y and z, with a distance of order p, we do have a substitute to the original Euclidean distance that removes a slight variability that is purely ancillary given the problem of inference. And so that's a possible choice. that, I mean, still incorporates the variability of the data, so you may think it's too noisy. But this leads to an improvement, as shown in this toy example. So we have mostly toy examples in the talk. And so if you take, say, a true data generating process that is a gamma distribution, but assume that your data is normal with those two parameters, mu and sigma, you can run the ABC on this problem. And using the Euclidean distance rather than the sorted distance does provide a worse approximation. So this is the pseudo value for mu and sigma, and this is the outcome of using the raw distance. So the gray curve is the density of the sample, while if you sort the data, you get something that is definitely better, especially on sigma. So even on this simplistic toy example, you can see the difference of sorting that removes some ancillary noise that you don't need to run the inference. And so that links to Wasserstein, because that's a specific case of the Wasserstein distance in dimension 1. That compares, so you have heard about Wasserstein already, the latest being Eric's talk, that doesn't compare samples as vectors, but as representatives of distributions. So it's a distance between the empirical distributions rather than the samples themselves. And so that's the entry point to this approach to ABC, that rather than looking at the samples as samples, we consider that they provide information about the distribution behind, and therefore use distances between distributions, which is another way of resorting to some non-parametrics, which is the validation for ABC anyway, that we don't know this complex distribution, and we try to find one way or another to estimate the distribution. And that's how you can validate ABC, even though it was not the case at the beginning. Okay. So a few words about the Wasserstein distance, or distances, because there are many versions of it, and the computational aspects of computing for real the Wasserstein distance. So I mean, this is a definition you have seen several times already, that the generic P Wasserstein distance is finding the joint distribution that minimizes the average distance between a realization from mu and a realization from nu by choosing the most favorable joint distribution on x and y. So it's a sort of copula setting where you try to find the optimal copula, with some conditions for this distance to exist, of course. Okay. And so if you do it, I mean, this is like a cartoon, very simple-minded cartoon to look at the problem. So if you do it in dimension 1, and if you have 3 realizations from the first distribution and 3 from the other one, you just want to figure out the minimization of the distance between those 3 points for both distributions, which are, in a sense, empirical distribution in that case. So you try to you have a matrix of costs, of distances between all those points, and somewhat obviously, if you look at the joint distribution that minimizes this sum, well, then unsurprisingly you have to force the original z's into different settings, which means that the joint distribution is actually restricted to having the pairs 1 and 3, 2 and 1, and 3 and 2 in this cartoon. That's a case where you just, I mean, the minimum is 1 known. But then, of course, you can generalize that to any setting, like in dimension 2 or further dimensions, and there are algorithms to figure out this thing. Now, I mean, this is very simplistic. Of course, there is the optimal transportation literature that is behind that is much more advanced, but that connects very naturally to the problem of bringing the two distributions together. And so, as I will mention again in a few slides, you can derive a full theory of inference in this setting by looking at estimators that are defined in terms of the Wasserstein distance rather than all other criteria. And in particular, you do find consistency results for estimating theta by this mean, namely that if, for instance, you have a sample here from the true distribution, and you look at the Wasserstein distance to a theoretical distribution, this will converge as the sample size grows to infinity. And then there is another step where if you replace mu theta by simulations from mu theta, then you do get convergence outward. So you can be purely empirical and still figure out convergence estimator at the standard rate. Okay. Now, of course, there is an opening in the theory of optimal transport since Cedric Villani moved to political functions. This is maybe the right time to engage into optimal transportation, which was a bit of a surprise, right? And so I won't go too much into the theory. I just have a few words about the computation of the Wasserstein distances. Namely that in dimension 1, the cost is in n log n. But when you move to larger dimensions, the cost increases to n to the 3, essentially, if you want to compute exactly the Wasserstein distance between two empirical samples. And so that's a bit much if you have a large sample, of course. And but there are alternatives that bring approximation to the Wasserstein distance, or the minimum of this quantity. One is through a regularization. It's called the Sinkhorn algorithm, and that reduces the cost from n to the 3 to n to the 2. So that's already some gain. And then there are other approximations that are more or less reliable and more or less fast. And there's a paper in Couturier that leads to an n log n convergence computation cost. And the dimension is not directly impacting this cost. But the one I want to mention and that we use in the paper is the Hilbert curve approach that projects back to dimension 1 the original d-dimensional problem, and that's what exploited by Mathieu and Nicolas in their red paper at the RSS to devise QMCMC method, quasi-Monte Carlo Markov chain method. And one of the advantages of this is that by reducing a multidimensional setting into a one-dimensional setting, there's a gain is obvious in the computational cost because we recover the n log n computation. So, I mean, this is a picture of the Hilbert curve that is the limit of this iteration process. But for computing the distance, we don't need to go to infinity. We just need to separate the data set so that there is a single projection on the curve. And so this Hilbert curve creates a connection between dimension 1 and multiple dimensions, as is this two-dimensional setting, that if you follow the curve linearly, well, you start at 0 and you end up, say, at 1. And any point in dimension 2 can be projected to the nearest version of the curve. And so you get a function from 0, 1 to the d to 0, 1 by this projection. And of course, if you're not in 0, 1 to the d, you use something like a logistic transform to get back to 0, 1 to the d. So, and that seems like a magical thing, because I mean, before that, I'd never seen Hilbert curve except in fractal settings, so it didn't seem at all connected with statistics. But that's a way to order any dimensional vector And if you do that for the real data and the simulated data, you do get a different type of distance between the empirical distributions for any distance rho and any power p. And so, I mean, this was using this paper, but this can be used for replacing the Wasserstein distance. Okay, so I mean, it is a distance. In the sense that it is zero if one is a permutation of the other. And so if you push epsilon to zero, I mean, the ordering, it doesn't matter for the distribution behind, so you can hope to get back to the posterior. And again, the cost per calculation is n log n, but there are side costs that may be non-negligible. So there is another version that is a swapping option that may reduce the cost as well, and both can be cumulated before using the Wasserstein. So, I mean, in the paper, we look at sequential approaches where we use one of these cheap versions first, and then when epsilon gets close to zero, we start computing the Wasserstein. Because one of the features of the Hilbert distance is that it brings an upper bound on the exact Wasserstein distance. But actually, it can be used per se as well, in that from an inferential perspective, you can prove some convergence result directly on the minimum Hilbert distance estimator. Okay. And so using one distance or another, we incorporate this approach into a sequential version where we refine the tolerance by using the previous simulations and the previous distances to derive the next epsilon, which would be epsilon t and not epsilon 1. So I mean that's the sequential version of W ABC, W being for Wasserstein, that we use. And I mean, there is nothing novel in this algorithm since you have already seen ABC, except that actually we implement the version devised by Anthony, the Hair-Hit MCMC, where we make several proposals and pick one of them by a special device to improve the convergence of the method. Okay. And so a few examples of that implementation compared with say standard ABC, mostly through toy examples. As we run the algorithm with more and more simulations, the distance to the posterior, if we used a sufficient summary, should get to zero. If you use the Euclidean distance, the noise remains important, and so with the same number of simulations, we stay away from that lower bound. But Wasserstein gets close to using the summary, so it gets close to the exact ABC in the setting for the same number of simulations, not the same simulation time. But you can see in this picture for 10 to the 6 simulations that we are very close to the posterior. And then if we move to larger dimensions, we keep that property that for the regular distance is I mean, keeps being worse than the Wasserstein one. Okay. And one last example here that relates to Louis' talk about the G and K distribution. So it's, I mean, the G and K distribution is a benchmark in ABC papers. Actually, it's still a toy example in the sense that we can compute the PDF numerically at a minimal cost. There is a very recent paper by Dennis that discusses an R package doing that. But you can extend it to larger dimensions because those are quantiles. So you can, I mean, merge them together through a copula and introduce any correlation that you wish. So it means that you generate for each dimension a normal, which is marginally a normal, so that jointly they are correlated. And then you transform them by this quantile function, and that gives you the multivariate G and K distribution. So it's a sort of toyish, if slightly advanced toyish example. But because you can run MCMC, you can provide a comparison of the two approaches. And with, again, the WABC approach, you do get, for most parameters, you do get outcomes that are fairly close with one approach or the other. It's only, I mean, there are things that do not work. The G and K parameters that, if you don't remember, are kind of hidden inside this transform of the normal quantile, are less well estimated compared with the scale and location AI and BI. So that's a well-known fact, but it may get really poor as in this picture. And well, I mean, regular ABC does worse than that, but I mean, it means that the ABC approach, even in this framework, has difficulties to infer about the G. While for the row, and again, it's not immensely surprising, we do get something that is close to the true posterior. Okay, just a few words about asymptotics before discussing this time series setting. So as mentioned earlier, there are convergence results if you look directly at the estimation problem. So this is extra away from ABC. There is an almost sure convergence. You can prove more than that with further assumptions, meaning a limiting distribution of the Wasserstein estimator. And again, that's at a root n speed. So this is slightly discussed in the paper. And just to show the comparison with regular MLE, if I take again my gamma example with my normal assumed model, this is the concentration of the MLE estimator compared with the one for the minimum Wasserstein distance estimator. And so they are fairly comparable because they both relate to the Kullback-Leibler distance. Okay. Now, if I move to ABC and Wasserstein, again pushing n epsilon to 0 when n is fixed, we do recover the true posterior, and provided you use a distance, a true distance, that doesn't matter. Now, if you push epsilon to 0 and to infinity, you cannot, if the model is not correct. I mean, using techniques that we use in the previous paper, so you can push epsilon to epsilon star, then you get the expected concentration of the estimated parameter on the pseudo true value, that is the value of the parameter that minimizes the distance to the true distribution. Okay. And so that's a sort of consistency of WABC that, I mean, the best you can expect is this kind of thing, assuming again that the distance goes down to this minimum at the right rate. And using existing results on optimal transportation, well, there are ways to evaluate the decay of the tail of the Wasserstein distance by I mean, known decay rates from this paper. So again, that's discussed in the paper. That's an illustration in, again, my toy gamma case as pushing the simulation time and further. That's how, I mean, the distance decreases with the simulation time. That's how it concentrates on the posterior. So you can see that in this toy example, you do recover eventually the posterior. And then, well, that's another example for the normal, just to illustrate the increase in the computation time as you push epsilon to 0. That, I mean, it grows very. I mean, this is a log scale. This grows quite fast with the number of iterations. So there is a point where you have to stop doing that. But after this 10 to the 6 simulations, you do get the concentration on the right quantity. Okay, so I mean, just a last bit to set you free, which is about the time series. So when you look at this distance between empirical distributions, or when you use empirical likelihood, there is this difficulty of what you do when the data is not IID, but is dependent one way or another, and dependent as in, for instance, an AR1 example. Well, in that case, you have to do some manipulation or dirty operations to get back to the IID case. So the first one is, I mean, this is the solution 0 in any problem. You just ignore the problem. And so you treat your time series as if it was IID. Okay. But of course, if you do that, there are parameters that you will not see. So in an AR1 model, you will forget about the phi. Okay. You can identify sigma square over 1 minus phi square, but not phi and sigma separately. And actually, the outcome of the Wasserstein ABC approach in that case signals this thing by concentrating on this curve in the log sigma phi space. And so that's, I mean, that's the best it can do in under those conditions by ignoring some aspect of the data. Okay. Now, of course, you can try to weaken this difficulty or this assumption by using lag vectors instead. So instead of considering yt as your observation, you just take the lags down to time t minus k, and then treat this as a vector and compare the distributions of this new vector, pretending it is IID when it is not, with the empirical version for the simulation. And if you do that for I think here a lag of only 2, because it's an AR1, you do get this outcome for your ABC simulation. That is, it does concentrate nicely on the true value of the parameter. And of course, pressing the lag to higher value would concentrate even further, but by increasing the dimension would take more time. And then there is a solution that we initially used in our ABC empirical likelihood paper with Kerry and Pierre, which is to just manipulate the data to recover the IID structure. So, I mean, considering that your data is a function of the parameters and of an IID vector, you invert this function to reconstruct the IID vector. So, for instance, in this cosine example of yt being depending on time and an IID noise, here it's, I mean, it's obvious that you can invert this equation down to wt equals this, and then based on the value of the parameter, you have these estimated residuals for which you can apply a standard distance. Okay. And of course, you can simulate from this example. So this is the outcome we get with this reconstruction. That well, it's very wiggly because we use several simulations, but as t grows, we do get in most cases an outcome that is close to the true one, or the true target, as far as we can say from MC-MC simulations. Okay. With some strange phenomenon that if we include the delay and the residuals, there is a temporary concentration on something that is not the truth, and then if we push further the seeing it is the delay, we do get down to the true value, which, I mean, we cannot explain very much why this is happening. And then there is a last solution that first I found very surprising, but that actually works probably better than the others, which is the curve matching, which is again to think that a time series is a curve, although you observe it in discrete time, and to compare the curves for your observed curve with the one that you simulate. And I find it surprising because I was saying that I find it surprising that it works because if you simulate one curve with the same parameters, you'd get all kinds of shapes. But somehow there is a recovery that, again, I cannot really explain. So, I mean, the notion is that the metric between on one curve and another is to not only compare the same value at time t, but also the distance of time. So you don't compare 2 points vertically, but you may compare them at different places in the space. And so in a sense, that's the comparison of the whole curve with the whole curve. And if you push lambda to 0 or infinity, you do get back and either the comparison of the points, or you forget about the indices and you back to method 1 or 0. And you should recover the posterior as you push epsilon to 0 again, presumably at a high cost in computation. But so that's an example of the same cosine toy example that while does recover quite nicely the posterior compared with the Euclidean, well, especially in that example, where the Euclidean distance totally misses the posterior. Okay, so that's the final slide. So, I mean, there are many things that still remain to be done, especially at the computational level, from my perspective, that and work is currently taking place on developing much more efficient metrics and computation algorithm to just lower the computational cost, which means that for reasonable sample sizes, Wasserstein becomes a feasible alternative to more standard ABC solutions. We do have, using essentially the same tools as with summaries, guarantees of convergence of the method as at least the sample size grows to infinity and epsilon decreases at the right rate. When the data gets more complex than those simple time series example, it's yet unclear how to devise corresponding Wasserstein distances, but there are works on Wasserstein distance for images, for instance, and so this could apply, at least in this setting, and presumably extensions to further models. I didn't discuss at all the dimension of the parameter because we didn't really study that in that direction. But that's of course an important problem. If the dimension of the parameter is large, what are the performances of the Wasserstein distance is not something that we can yet master. Thank you for your attention.
Questions for Christian?
So maybe you mentioned it, but I missed it. So you said that it's the method is consistent for IID data.
Yeah.
But I mean, it should be consistent also if you have invariance permutations, right? I mean, if you have kind of exchangeable data.
Yeah, it's exchangeable. Yeah.
So you need
what you need is to approximate consistently the empirical distribution. So IDness is definitely not necessary. Yeah. No, that's true. Yeah.
Is there a way of connecting the distance, or the transport distance, to the generative process? Because the only thing you know is the generative process.
Yeah.
So, I'm just thinking of that for your AR, because there it's a time series you're using the time. When if you were completely blind, you would have known that your generative process was doing things in time somehow, with that. I just, I'm just thinking, if you think abstractly of a generative model, is there something that could be done along those lines, which would be beautiful, because then it would be applicable to, I don't know.
Of course, I mean, in this time series context, you can always go sequential and follow the process and compute the distance at each time. So you could gain time by...
No, but I'm thinking that, you sort of modified your transport by having this idea of neighbors. Okay?
Yeah.
So this is, you get that idea of neighbors, you could get that from your generative process.
If it's not too much of a black box. When you have, for instance, you have to imagine that your generative process is in the time series is delivering one value at a time. But if it's really a black box, that would be complex. I mean, but one thing is,
typically it has some structure.
yeah.
So for the GNK example, would there be a transform of the data that might be more informative?
Yeah, well, in a sense, if you could reconstruct the normal behind, and then you would get the Euclidean on the normal transform. So I think in the GNK, yeah, you can go that way, yeah. And maybe even produce, because what I was thinking of your question is that you were asking whether we could directly simulate the Wasserstein distance, which is something that would be fantastic for any ABC method, that you could, if you could directly simulate the distances, this would kill the dimension, and so this would kill a lot of computational time. But so I think for the GNK, I've not looked at it, but my intuition is that you could compute directly the distance, exploiting the normal behind it, given the parameters.
Mm-hmm.
But yeah, that's something to be. Maybe that could be the fifth method, something projecting back to improve the distance. Yeah.
Yes. Maybe I missed that part. What is the epsilon star there?
Epsilon star is in a misspecified model. It's not zero.
Okay.
That's
So that's
in short, that's because you cannot get closer than epsilon star to the true model.
Oh, okay.
That was defined quite a while ago, and I don't think I see. Sorry. It's not there. Anyway, that's the minimum distance you can find, and that's the value of this thing. For the minimum theta, that's the distance. So it's like in a Kullback library distance. You cannot get closer than a certain quantity if the model is not in the family.
Okay.
So that's incorporating the case of any specified model. But if the model is well specified, that would be zero.
Okay.
Yeah.
Yeah. Okay. So it means your generative model may not be the same as your true model.
No.
So that's the distance.
As in the gamma example, for instance. So you cannot. There is a value of the parameter that brings you as close as possible, but it's not zero.
Yeah.
And so that's the formalism that you can use to study misspecified models.
Yeah.
Thank Christian again.